Welcome to Chapter 6 for Trigonometry. So all of the notes for Chapter 6 are all together. They're all basically over the same concept, just talking about the different types of trig ratios and how they relate. So we have seen what we're going to talk about in a couple different ways, in a couple different classes. But now we're going to relate it all back to our unit circle and our trig functions, okay? So the big topic for Chapter 6 is talking about what we call our inverse trig functions, okay? So we have seen this before in geometry. When we did our SOHCAHTOA, we saw it as this inverse sine, inverse cosine, and inverse tangent when we might have had two sides of our right triangle, and then we're looking for that angle. That's when we used our inverses, okay? These can be found on your calculator if you hit the blue second key and then your sine, your cosine, and your tangent functions. So that's where you saw it in geometry. If you have taken Algebra 2 already, you may have seen these, the inverse already in Algebra 2. So what it would look like for you in Algebra 2, let me slide off to the side and kind of show you for a second. So you might have been asked, like let's say we had the function y equals 3x plus 2, and you were asked to find the inverse of this function. So whether you've seen this or not, it's a pretty simple concept, okay? All you have to do is switch your x and your y. So wherever you see a y, you now put an x, and wherever you see an x, you put a y, okay? So you flip them, and then you solve for y. So we would subtract 2 from both sides. Oops. Subtract 2. And then divide by 3. Okay, so this function and this function, those are what we call inverses of each other. Okay, another way you can think of your inverses is through points. So if you had a function and you found the points that are on that function, or if you were just given a set of random points, like let's say, I don't know, 1, 2, 2, 3, 3, 4. I don't know, completely made that up. Don't know if it makes a function actually, but let's just say that's our function. In order to find the inverses, we would just have our x and our y switch places. Okay, so they would stay the same sign. I don't have any negatives here, but if we had negatives, they would stay the same sign. So instead of 1, 2, this would be 2, 1, 3, 2, and 4, 3. Okay, so then you would be able to graph those new points, and that would be your inverse function there. Okay, so when it comes to talking about our inverse trig functions, it's kind of a similar concept. Basically, all we've done is we've taken our x and our y coordinates, and they're going to switch places, right? We know how to graph the sine and cosine function from Chapter 4. We already went over that. So now it's kind of resurfacing in a different sense. So if we were looking at this in the coordinate plane, okay, notice our x-axis and our y-axis, they've now switched places, okay, because we're switching our x and our y values, so we're switching that scale. So for sine, right, our first point was always at 0, 0. We always started at the origin, so it makes sense that when we flip this, our first point starts at the origin again, okay? But if we think about, okay, what about our first point, right? Our first point always went to pi over 2, 1, right? We started going up that first mountain. If we flip that, that now becomes 1 pi over 2, which is now this point right here. Okay, so what that would look like in terms of sine is maybe we were asked, okay, the sine of theta equals 1, right? We know our output, we know our y coordinate is going to be 1. Now we're trying to work backwards, okay? We're doing the inverse. So now we're asking ourselves, okay, if we knew that the output originally was 1, what did that input have to be? Because that input is now our output because they're switching, okay? So what this would look like is if we took the inverse sign of 1, our output would now become pi over 2 instead of the sign of pi over 2 equals 1. So they're just kind of switching places, right? Our input and our output are now switched. Okay, so if we think about that same idea in terms of cosine, remember cosine, our very first point, always started up above our y-axis. So our original point always started at 0, 1, but now this point switches to 1, 0, which is right here. Okay, so just slightly different, but it's just kind of the same idea. We're just switching now from on the y-axis to now on the x-axis. Okay, so we would see this as, okay, we know that the cosine of theta is equal to 1. Now if we take the inverse of that, what is our output? Where does the cosine equal 1? And we would get 0. Okay, similarly, if we thought about the cosine of negative 1, the cosine of theta equals negative 1. If we took the inverse cosine of that, we think about, okay, where does the cosine equal a negative 1? So where does x equal negative 1? And that would be on the y-intercept, on the unit circle would be 0, okay, which would also be 180 and pi. Okay, so let's think about this in a couple different scenarios here. Let's write it out a little more in depth for ourselves, so maybe it'll start clicking. Okay, we've seen this, we've kind of talked about this a little bit when we started switching into radical form back in chapter 3. We looked at, okay, if we knew that theta was, or if we knew that the cosine of theta is this, what did theta have to be? Okay, so for example, our first one's going to be if the sine of theta equals 1/2. Right, to pull that sine off, forgot to show this, to pull that sine off, if you remember, we take the inverse sine of sine, we just get x. And if we take the sine of the inverse, we again just get x. So they're opposites of each other, so they pull each other off if we do the other one. Okay, so if we think of the sine of theta equals 1, so hopefully in your head you're thinking, okay, now instead of plugging in an angle and getting a point, we don't know the angle, right? That's our unknown. So when we take the inverse of 1/2, we're trying to figure out what is that angle, right? Our point is now getting plugged in, and our angle is now our output. They're just switching places. Okay, so if you see the inverse sign, so you might see this a couple different ways. You might see the sign of something, and you know that you're going to work backwards, or you might see it just written as the inverse sign of 1/2 equals what angle, and you have to know that your answer is now going to be the angle. Okay, so if we think about this a little differently, hopefully we're thinking, okay, well, sine of theta, it's positive, right? It's a positive 1/2, which means that y equals a positive value, right? Because sine always goes hand in hand with the y coordinate. Okay, y is positive in quadrant 1 and quadrant 2. So we're really just looking at everything above the x-axis. Okay, so where does our y coordinate equal positive 1/2? Okay, that's our question. And hopefully we remember that it's going to be here. Oh, wow, that's not great. Here and here, which was at pi over 6 and 5 pi over 6, right? These points would be negative square root 3 over 2, 1/2, positive square root 3 over 2, and a positive 1/2. Okay, so our answer would be pi over 6. We don't have to put a, we can just put a comma, 5 pi over 6. Okay, so what's also important to know about this is if we're talking in terms of the unit circle, we know that the radius is always going to be 1, and we already know these points around the unit circle, right? So we're just thinking about them in terms of the x and the y-axis. The other connection we can make, and this becomes important when we move off of the unit circle, is that these two angles have the same reference angle. And if you remember way back, our reference angle means it has the same distance from our x-axis, right? These both would have a reference angle of 30, because this would be pi over 6 is 30, and 5 pi over 6 would be 150, and their reference angles between the x-axis would then be 30. Okay, so let's try a different one. Similar, but a little different. So what if we had like the cosine of theta equals 0, right? We would still take the inverse cosine of 0. So we're asking ourselves, right, where does the cosine function equal 0? And remember, cosine always has to deal with x. So where does x equal 0 in our unit circle, right? X is going to have a coordinate of 0 if we are staying on the y-axis. Okay, so those angles on the y-axis would be pi over 2 and 3 pi over 2, right? We're not moving anywhere to the left and to the right. Okay. All right, so a little different. We also still need to talk about tangent because that's always super important. So what about the tangent of theta equals 1? So if the tangent of theta has to equal 1, that means we need to figure out what the inverse tangent of 1 is. Okay, so there's a couple different avenues we can take. Remember, tangent is y over x, and we need this ratio to be equal to 1. So if y over x equals 1, that means that x has to equal y, right? Because the only way we can get a fraction to be equal to 1 is if the numerator and the denominator are the same. Okay? More importantly, it's a positive 1. Okay? So if it's a positive 1, okay, in order for our x and our y to have a positive value, then this point also needs to occur in quadrant 1 and quadrant 3. Okay, so if we think about in quadrant 1, at what angle do we have an x and a y the same? That would be pi over 4. And then when we think about it in the quadrant 3, right, we're going past our pi, so it's going to be between pi and 3 pi over 2, which is 5 pi over 4. Okay, so similarly, if we kind of do the same thing, when we think about this as a negative 1, that means these points need to be in quadrant 2 and quadrant 4, because that x and that y need to produce a negative 1 instead of a positive 1. So in quadrant 2, where our x and our y are the same, producing a negative 1 would be 3 pi over 4. And in quadrant 4 would be 7 pi over 4. Okay, all just again looking back at our unit circle there. Okay, so let's just kind of create a cheat sheet for ourselves. So if we're talking about cosine, right, cosine is always dealing with x. We're always focused on that x coordinate, okay? So we're thinking about x equal to some sort of value, okay? Back in Algebra 1, when we learned how to graph lines, we learned that if we ever had x equal to a value, this produced a vertical line, right? A line running straight up and down with an undefined slope. So when we create this vertical line with an undefined slope, this vertical line either has to run through quadrant 1 and quadrant 4, or quadrant 2 and quadrant 3. Okay, we would be in quadrant, We'd be in quadrant 1 and quadrant 4 if our value is positive. We'd be in quadrant 2 and quadrant 3 if that value is negative. Okay, similarly for sine, we're only dealing with our y-axis. So we're looking where y is equal to some sort of value. So this is creating a horizontal line. Okay, so when we're creating a horizontal line, the y is going to be positive when we are in quadrant 1 and quadrant 2. Okay, so you would want to find two values in quadrant 1 and quadrant 2 if the value is positive. And then quadrant 3 and quadrant 4 if the value is negative. Okay, the tangent's a little different, right? Because the tangent is y over x. So that changes things, right? Because now it's a relationship between the two of them. Okay, so let's say maybe like y over x equals 6. Okay, if we wanted to solve this for y, we'd multiply both sides by x, and we would get the equation y equals 6x. So then we would follow the line of y equals 6x to figure out where those values lie. Okay, majority of the time for the tangent, you're going to have the combination of quadrant 1 and quadrant 3. And then quadrant 2 and quadrant 4, because it's going to be some sort of diagonal that crosses. Okay, so let's do just one more example of something similar that you might come across, okay? So let's do something a little different. Let's say like the sine of theta is going to equal 7/8. Okay, if we were going to take the inverse sine of 7/8 to find out what angle that produces, that's not going to work for our unit circle, right? It's not going to create some nice point, right? Because we already know that it's usually going to be like 1/2, square root 3/2, 1, square root 2/2, right? We know those values that keep reoccurring when we talk about our x and our y coordinates in the unit circle, right? So obviously this is not on one of those, but we can still figure out what the value is. So what we can do is we can always type in that inverse in our calculator. So if you go to your calculator and you type in the blue second key in sine, and then do a fraction of 7/8, you should, if we round it, get a value of 61.0. I know it's more of a decimal than that, but we'll just keep it at 61 just to make it nice for ourselves. Okay, so what this is saying, I said this a little bit ago in the video, is that this value is telling us what our reference angle is. Okay, so our reference angle, remember, is that distance from the x-axis. Okay, so if sine is a positive 7/8, okay, if sine is positive, that means y is positive, and therefore y has to be positive in only quadrant 1 and quadrant 2. Okay, so if we think about our graph, that means we have maybe an angle something like this-ish, and maybe like this, right? I know they're not perfect. I know they're not. I'm not getting a protractor out to measure them, but you kind of get the idea. We're having some angle jut out at quadrant 1 and some angle jut out at quadrant 2. And remember, to find the actual angle, we know that their distance from the x-axis is 61. So to find the actual angle for quadrant 1, we know it's just going to be 61, right? Because it's going from 0 to 61, and that's our angle measurement. If we're looking in quadrant 2, okay, remember to find an angle in quadrant 2, we would do 180 because that's where the x-axis is. Minus 61 would give us 119. So our answers, right? What is theta when the sine is equal to 7/8 would be 61 and 119. And that is chapter 6.